Hey guys, okay, so over the next few days we will be making a couple of videos for regarding the CBSE topics for science and maths. Now these videos are meant for people who don't particularly listen in class, and I urge you all to not use this as your study material. Just use this as your reference material for the exams. By the way, this is for the third term only. Okay, so today we will be going over chapter 5, that's periodic classification of elements. Now firstly, why do we need a periodic classification of elements? Well, it makes it easier to understand the properties of elements, and let's face it, it's more easier to learn the elements that way. I mean, it's easier to learn a bunch of sorted items than to learn a bunch of unsorted items, am I right? Alright, so now many attempts have been made to classify elements. One such attempt was in 1817 by Johann Wolfgang Dobernier. His theory was that when three elements in a triad were written in the order of increasing atomic mass, the mass of the middle element was roughly the average of the masses of the atomic masses of the other two elements. Say you have calcium, strontium and barium, that's Ba, Sr and Ca. Alright, now the atomic mass of Ca is 40.1 and Ba is 137.3. And now strontium is 87.6. Now if you were to take a calculator or just do the math yourself, you get like 40.1 plus 137.3, 4.71. Alright, and let's say divided by 2. Alright, so 2 divided by 104, 17. Alright, so after you actually divide it, you will get 88.7. Strontium is 87.6. So like I said, it's roughly equal to the average of the other two atomic masses. Next, Newlands, he tried to classify the elements as musical notes like sa, re, ga, ma, pa, de, ni. However, oh yeah, by the way, he had thought of this he had given the idea in 1866. However good this idea was, it still had quite a few defects. Like, for example, it only worked for lighter elements. Next, during Newland's time, only 56 elements were known, so he had made this according to those 56 elements. And finally, he had to adjust two elements inside one slot. Like, for example, you have cobalt and nickel, they come under Sa, or cesium and La, I forgot what that stands for, comes under Ma. And finally, you had elements like cobalt and nickel in the same slots, but for example, cobalt, it has similar properties to iron, but it is placed on the opposite end of the table. Next, we move on to Mendeleev's periodic table. Now he had the right idea, but he just chose the wrong reference. He should not have gone with atomic mass, instead atomic number, but he chose atomic mass. However, his table did turn out pretty well, I'd say, but it had its own defects as well. Again, during his time, not many elements were known, but elements that are known now were not known then. Then elements such as cobalt and nickel, their atomic masses are cobalt's atomic mass is slightly greater than that of nickel, yet it is placed before it. And finally, you have hydrogen. hydrogen was not given a proper place in the periodic table. And finally, isotopes. Isotopes were not known during his time, and when they were known, they posed a challenge to Mendeleev's periodic law. However, even though his table had these demerits, he did actually predict 3 elements that would come, like you have, for instance, Eka boron, that's scandium, Eka aluminium, that's gallium, and Eka silicon, that's germanium. He actually predicted that these 3 elements would be found in the future and left space for them. Alright, now we are moving on to the major stuff. That is the actual periodic table that we are currently learning, the modern periodic table. Now, the person who made this had used the atomic number of the elements as the criteria for the classification, and in the end, his table consisted of 7 periods and 18 groups. And of these 18 groups, 4 blocks were formed: S, P, D and F. Now F blocks are like lanthanoids and actinoids, that's at the bottom, where you have cesium or neodymium, yes. And then P blocks, that's elements of group 13 to 18, like helium or boron, carbon, all of these. D blocks, which came from the 3rd group till the 12th group. They were also called the transition elements. And finally you have S block, that's group 1 and 2. Now group 1, it has all the elements in group 1 together have a common name called alkali metal, while group 2 has alkali earth metals, and group 17 collectively are called halogens. And finally group 18, noble gases. Alright guys, let's go for the trends of the modern periodic table. Well, first of all, let's go down a group. Down a group, the number of shells increases, which in turn increases the size of the atom, or basically the size of the atom becomes bigger and bigger as you go down a group. And from left to right along a group, the valency increases along with the atomic radius decreases due to increase in the nuclear charge. And the nuclear charge, basically higher the nuclear charge means closer the closer the electrons are towards to the nucleus. Alright, now we move on to metalloids, which by the way is the final topic over here for this video. Metalloids are basically the elements present along the zigzag line that separates the metals and the non-metals in the periodic table. They include boron, silicon, germanium, tellurium, and much more. Not much more, 3 more. This is because they show both metals and non-metallic properties. So they can be called either both semi-metals or metalloids. That's it. And if you've been listening, you should know how to pronounce Dobereiner, which I still don't know how to pronounce. Sorry, by the way. Anyways, his triads, then the Newland's law of octaves, Mendeleev's law of atomic mass, and then the modern periodic table, which is classified based on the atomic number of an element. And of course, yeah, the trends of the modern periodic table. And finally, what are metalloids?